In this example, we're going to work with a concept from chemistry, the ideal gas law. And the ideal gas law states a relationship between the pressure of a gas, its volume, and a few other constants over here. N is the amount of gas there is, measured in number of moles. R is the ideal gas constant, which translates between these various units. And T is the temperature in degrees Kelvin. What this relationship captures is increases in pressure have to be traded off somehow against either the volume here, the number of moles, the amount of gas, or temperature, and vice versa. If we change the temperature, there has to be a corresponding change in one of the other values in this scenario. For our particular story, we're going to be looking at a case where we have 0.1 moles of gas, and that would be our N. Those are held in a piston, so imagine some circular chamber like this, and we're going to hold the temperature constant. So what's going to happen is our temperature is constant, and we're likely going to be playing pressure against volume. The piston itself is going to move to decrease the volume from 3 liters to 1 liter over 60 seconds. So imagine this is a piston, and we have a rod attached to it. This is going to move inwards so that we decrease the volume. What are we being asked to analyze or predict? What is the pressure halfway through this process when we're exactly at 2 liters of volume? And the related rates question, at what rate is the pressure changing at this time? More formally, we're being asked for P of, let's use T as our time in seconds. We're looking for P of 30 because 60 seconds is the entire time. And we're also asking for the rate of change of the pressure against time at 30 seconds. In this particular scenario, when we're looking for the derivatives, we know a relationship that's always true. This is the ideal gas law, so it's something we can rely on. And we're going to start with it. So P times V, pressure times volume, equals nRT. What we want to do is take the derivative of that to find the derivatives dp dt. However, we need to differentiate all the terms in this expression. One thing we should note, though, is that we are keeping the number of moles N constant. We're also keeping R constant because it is the ideal gas constant. And last but not least, we're also holding the temperature constant. That's not necessarily guaranteed in other scenarios, but here we're maintaining it at 0 degrees Celsius or 273 Kelvin. What that means is when we go to take our derivative, we're taking the derivative with respect to time of both sides. The derivative of the right-hand side will simply be the derivative of a constant, which gives us 0. On the left-hand side, we've been explicitly told that the volume is changing with time. We're shrinking the volume, and as an implication, the pressure is also going to be changing to match that. As we shrink the volume, the pressure is going to have to go up. So both of these are functions of time, and so we're going to need to use the product rule to compute this derivative. But that's fine. Take the derivative of the first, dp dt, times the second, and then we're going to add the first p times the derivative of the second, dv dt. Perfect. So now we have a relationship that involves the derivative that we want. This is our goal. The only ingredients missing, we're going to know our volume in a second. We can probably figure out the pressure. It's one of our intermediate goals. And we need to know dv dt as well. All right, so again, this is our goal here. Let's figure out this dv dt on the side. The problem tells us we're decreasing the volume from 3 liters down to 1 liter. And so we are losing 2 liters of volume. And it's taking us 60 seconds to do that. And a quick unit check. The units of the derivative of volume with respect to time should be in liters per second. And that's in fact what we get here. We use lowercase l. And we can simplify that to -1/30 liters per second. So now we can actually start solving for this. The rate of change of pressure times volume is going to be -P dV dt. And if we divide by volume, we can find dP dt is going to be negative the pressure over the volume times the rate of change of the volume. And that's what we're going to take over to the next page and start filling in the last ingredients that we need. Here we have our formula for the rate of change of the pressure. Here we have the known rate of change of the volume. We also know that the volume at 30 seconds is going to be halfway between 3 liters and 1 liter, so it's going to be 2 liters. The one missing ingredient is the pressure at 30. And for this, we need to return to the original formula and take a look at that. PV equals nRT at time 30, that 30 seconds. We're looking for this. We know this, and we can figure out all these other values, or they're given to us. So let's actually summarize. The pressure at time 30, T equals 30, is going to be nRT. Those are all constants over the volume at that moment. And we were told the number of moles was 0.1 moles. The constant that goes with the units we're going to be using is 8.31. The temperature is 273 degrees Kelvin. And the volume at time 30 is simply 2 liters. If we multiply that all out, we get 113.43. And the units that go with this 8.31, the units of pressure are in kilopascals. So when we get this completed, we have a value for the pressure, and now we can sub in all of these values. And the way we often write this is the derivative, rather than putting a bracket in here, often it's written with this vertical bar, which is a little more transparent. It says explicitly we're plugging in a value. And when we have that, we're going to have -113.43 over the volume, which is 2 liters, and dV dt was our -1/30. There we are. And now we just calculate that value there. And we obtain a positive value, 1.8905. And the natural units on this expression would be the units of pressure, which are kilopascals, and the units of time here, which were seconds. So the pressure is increasing at roughly 2 or 1.89 kilopascals per second.